computer and annotate and spotlight. So this may be one of the most technologically relevant lectures that we will have, less than any other lecture that we have had during the whole semester. We have been building up things in actually to be able to get to a level like this. It's so let's dig into it. Okay, so this is how we ended the last lecture with this graph here. And let me remind you, what does it mean? When we have a bunch of atoms completely separated from each other, meaning R is very large, and we have many atoms. And what I want to do is see how do we change the energy of the system of the electrons when I start bringing these atoms together. So when I have them very separate, you can actually extend this line to infinity here, and you will have energy levels. And those energy levels are going to be the energy levels of an individual atom, because that atom in particular won't feel the presence of all the other atoms. So there's, it's almost like an isolated kind. As soon as the atoms start seeing each other, we have this phenomena that there's we have two important effects when what does it mean that the atoms see each other? I mean, that is simply the fact that the electronic clouds of ones are starting to see the electronic clouds of the other, because otherwise these are neutral entities, and as a neutral entity there's going to be no electromagnetic interaction between them. The atoms are essentially that. Okay. So what happens when the clouds start seeing each other? We have this phenomena that we were seeing before, that let's say we have an electron, we have two potential wells, and we have each of these potential wells has an electron on it. And when I start moving it apart and form a big potential well, now the electron can move in both of them with twice the length. The energy of the system goes down. So I change the quantum mechanical system by doing that. This is exactly the phenomena that occurs here. And essentially one state, what does one state do? This start lowering the energy a bit when you get to arrive to a certain point. And not only that, if the energy is lower, you can get many linear combinations of these things, of the wave functions of the electrons, and you actually generate a range of possible values for the energy. So you get instead of having simply a level, you start getting a band of allowed possible values of energy. And what this graph here intend to represent means that the electrons that are higher in energy, meaning closer to the Fermi level of the atoms, when you have in a crystal, they start forming this band structure here, meaning this is a region of allow energy values for this particular level of the atom. When it's completely separated, when I start closing up, I have a range of value. Here I have a smaller range of value, and here I almost don't see anything. I don't see the generation of a band. So this effect of the electrons overlapping and seeing a benefit of actually lowering the energy by making linear combinations among them, it's more strong when the atoms see each other, when the electrons see each other. They see the exclusion principle, in action. These guys over here are very deep in the core, and they see no difference. So they retain their atomic character. So this guy seems to ignore the fact that you are getting all the bunch of atoms together in a crystal. Okay. So if you know, if I end the thing is this guy's over here, this is sort of this energy bands actually start going up at the end, because it's not only the benefit of because you can see that if you bring the atoms together, there's going to be this mix in energy. The energies in the Fermi level of each of the atoms are going to go. They have the advantage of going down because they are closer, so they are less bound than before. So the energy is lower. So this is good. But then if you keep pushing the atoms in, eventually you will have a nuclei completely positive, seeing a nuclear completely positive, and this is very high energy, so there's going to be a repulsive energy. And this is why these energy bands tend to move up at the end, okay? So the whole system becomes repulsive when you get closer together. The fact that this thing actually goes down when you are bringing it together, that's what makes this system stable. So it's better for the individual atoms to actually form a crystal instead of being separated by themselves, because the system will lower the energy when that happens, okay? So this is sort of the picture that one wants to keep in mind. So the states deep in under the equilibrium separation, which is this one over here, the states deep into the core of the atoms will be not affected. You will have just an energy state, and as soon as you go up very close to the Fermi level of the atom, you are going to start seeing that there is a band, there's a region of allowed energy values, where before there was a single value of the energy for each atom. Now the combination of the orbitals of one with the other, makes a band like this, okay? That lowers the energy in principle, which is the benefit of it. And the stronger the effect of the width of the band is, as the electron, the energy gets higher. So the higher the energy, the larger the width of the band, okay? The band meaning the region of energy, of possible values of energy for the electrons in the system. What we were doing in the last class was actually looking at, let's say this is the most external one. We're saying this guy actually goes to infinity, because what I have here is almost a free electron moving inside a complete box. So in that approximation, this guy would go to infinity, and you will have all the possible values of the energy for the electron. In practice, it's not like that, but we gain some insight on the properties of this material by looking at that, and how the energy feels, how the electrons are feeling these states here. And we actually learned that the important difference is that instead of the Maxwell-Boltzmann factor, we have to introduce something that allows for the exclusion principle to work, which is the Fermi-Dirac distribution for the distributions of the electrons in the system, okay? This type of band structures that are very general, they can be classified in a way. You know, we have things like this. For example, we have a situation in which the electrons are in the bottom band here. This is the one that is completely filled, and the one on top is completely empty, and there's a region of energy values that are not allowed. So this is what is called the energy gap, okay? So if this value is large, it means that that this thing is an insulator, okay? Why is this an insulator? Because the only way you can get if this is a field band, there's no room for an electron to move there, because if you want to move an electron, you have to move it to an unoccupied level, an unoccupied level with a higher momentum in certain direction. But there are no unoccupied levels here. They are all occupied. So when you have a system like this, this is an insulator. Okay, this is what makes glass or an insulator. You know, silicon dioxide. It has a very large energy gap. How large it is? You know, you can put all the visible light through it. So it's close to 4 electron volts. The energy gap in that material. And how do you get to? Can you make an insulator conductive? Yeah, you can. How can you do that? You have to promote an electron from the valence band to the conduction band. This energy band here is where allowed energy values are. So I can put an electron here, and if I put an electron there, I can put some sort of electric field on this thing, and this guy is going to move. But how do I put an electron there? Well, one thing that you could do is expect that it will happen because you raise the temperature. So what is the probability of having an electron here? Well, it's exactly related to the Fermi distribution. And it happens that the Fermi level for a situation like this is exactly in the middle of the gap here. And the Fermi distribution, we're going to get to that. You know, it's a very small value if this is a large energy gap. So it means there are barely no electrons up here if this energy gap is big. If this energy gap is small compared to the temperature, you will have a lot of electrons here at room temperature. If that happens, this guy will conduct some electricity. Okay, and how will do that? Well, you can move these electrons around, and it happens that the electrons excited in this band actually leaves behind holes in this sea of electrons here, and the conduction of this material is which is a semiconductor, has to do with the motions of the electrons in one direction and the holes in the opposite direction. And if that taken into account, that gives the total energy of, not the total current that a system like this can hold. Okay, so the first thing is large energy gap, insulator. There are no electrons to be moved. This guy, there are some electrons that could be moved because some of the electron can be in here. And this is the third case. And the third case is that you have this filled band and you have this partially filled band here. If you have this partially filled band, you have a lot of empty states very close to where the highest occupied level is. So essentially, when you put an electric field, you can give to all these guys here, you can move them. All these guys, the ones down here, nothing. They're going to be completely filled. But these guys here are going to be able to move to an unoccupied state with higher momentum because they are available for them in the band. Okay, with higher energy, and they will be able to move. So this is a situation when you have in a conductor. This could be copper, for example. You can have and the properties of copper are actually could be well described by a partially filled band, like in this particular case. Everything that happens down here, it doesn't count. Whenever you have a full valence band, this is not going to contribute to conductivity in any way. Okay, so no transport of charge is produced by a field band in these materials. This is a good approximation for a metal, and actually for a metal, you can actually say this electrons here, this density of electrons here, I could actually think of them as being a free electron metal. Meaning the model that we will look at in last class. See that it's filled up to a certain level. This level is the Fermi level, and they are unoccupied up here. and you can apply a field, and this thing is going to move, and then this thing, the height of this energy level with respect to the bottom of the band has to do with the density of electrons in the system. Okay, that's the key part. Okay, I wanted to actually consider an example that was put in the book, and I'm copying it here, and I'm trying to, because there are some numbers here that are meaningful. So it says, consider a material with a band structure described above. I don't know which is the band structure described above, but it's a semiconductor. Okay, with the Fermi energy in the middle of the gap. As I told you before, the Fermi energy we're going to consider in the middle of the gap. And the question is, find the probability that a state at the bottom of the conduction band is occupied at T equals 300 and at T equals 310 for these different values of gap, 0.2, 1, and 5. Okay, so I have something that is very semiconducting, a reasonable semiconductor, and an insulator. Okay, something that is 5 is almost an insulator, and we will see why. So this is the model that I have. Okay, the model that I have is I have electrons down here. I have some electrons here are going to be thermally. This is why this line is sort of orange, thermally excited, and they are going to be up here in the conduction band. This is EC, this is E valence, and the Fermi level is exactly in the middle of the gap here. And the Fermi function that actually corresponds to the probability of one state here being occupied is the one that I'm showing here. This is the expression, but if this is a poor graph, but anyway, this is the energy scale. The bottom is the energy scale. This and the value of F corresponding to the different values of the energy are shown here. So for energies very far away and below the Fermi level, this is 1. And then depending on the temperature, this thing could start going down and have this exponential form. If the temperature was 0, if the temperature was 0, look what happened here. If the temperature was 0, this thing over here is E divided to 1 over 0. Beta is 1 over kBT. Okay, and this expression is, I should have, okay, you know, the beta is 1 over kBT. I should have told you that before. I think I wrote it down in last lecture, but it should have been here. So 1 over 0 is infinity. So E to the infinity is equal to 0. So when would that be 0? It would be 0 if E is greater than EF. So essentially, it gives this step function, which is 0 here, and if E is greater than I'm sorry, less than EF, this thing jumps to 1. Okay, so the trace that I'm doing with the pointer here is showing this should be the form that the function have when the temperature is 0. When the temperature is higher, you get this smooth transition from this place to that place over there. Okay, so essentially at T equals 0, the probability of having an electron in the conduction band will be 0. Okay, because the step function will kill everything in the conduction band. And it makes sense because all the system will be occupying the low energy state. If now I activate the temperature, you know, I give the possibility, I raise the temperature, I give the possibility that some of the carriers here will be found up here. Okay, and this is the meaning of having a finite probability here with this sort of distribution. And what I have done here, I have tried to answer the question that was posed. I have here the gap energy, 0.2, 1, and 5. And here I have the temperature, 300 and 310. Okay. And in order to have an electron here, you need to this exponent here this is the thing that I have to evaluate. The energy will be equal to EC. Okay, EC is the bottom of the conduction band. Okay, and this is the axis of energy. So 0 is down here. This is EF. This is EC. And this expression says take E and subtract it from EF. I want the electrons to be here. What is the probability that there's an electron there? Is then the difference EC minus EF. But EC minus EF, I know that is equal to the gap energy divided by 2, because the Fermi level is located in the middle of the gap. And the gap is equal to EC minus EV. EC minus EV is equal to gap, okay? And I know that the Fermi level is in the middle of the gap, so this distance here from EC to EF is E gap over 2. That's what I'm saying here. So the term that goes to the exponent is E gap over 2 divided by KBT. And what I have done, I have evaluated this expression, F of E. These are the values of F of E for all these cases. One with each of the gap energies and with the 2 temperatures. And look at what happens here for the very low difference with a very low gap energy. This is a sort of this is a 2% of the probability. It's almost 0.002 that you will find an electron here. And if you raise the temperature by 10 degrees, this value actually, what does it mean increasing the temperature? Increasing the temperature, it means that this thing becomes more flatter in that way. So the height here is higher. This is reflected here, okay? And this is 13% larger than this, only by 13 degrees, okay? If the difference is 1 electron volt, look what happened with the probability. The probability goes to 10 to the minus 9, okay? Even though this is almost, 100% difference between this guy and this guy is twice the value, almost, from the 310 to, so there's a large increase. The numbers are very small, okay? This is 10 to the minus 9. If you go to 5, 10 to the minus 42, meaning this is nothing, meaning that there's no probability of finding an electron on top there. This is, manageable, because it really depends on the number of electrons that you have down here. If the number of electrons is 10 to the 18th or something like that, or 10 to the 20th, which is Avogadro's number. If you have an Avogadro numbers of electron, then you will have a reasonable number in the conduction band. You will have a reasonable number of electrons up here, meaning 10 to the minus 9, the Avogadro number, which is anywhere 10 to the 15 or 16, pretty much good for making somebody some decent current. But with this 10 to the minus 42, there's no chance. Okay, this is almost like a metal. You'll see a lot of electrons up here if you have a band gap of only 0.2 electron volts in the material. Okay, 1 electron volt is nearly the band gap in silicon. Okay, so this is something to keep in mind. This is a typical insulator. Okay. Now we were only calculating the probability of finding an electron here. We also know that we could calculate the total number of carriers, electrons, in the conduction band by saying n is this total number. I will have to integrate from the bottom of the conduction band from here to count, because there's one that it could be the probability of having one excited there, one excited there, and there. As long as I go higher and higher away from the bottom of the conduction band, the probability will decay exponentially. This is what it says here. This is an exponential function. So, but I can calculate the total number by integrating this function times the density of states of the system. And what is the density of state? Well, it is fairly similar to the density of states that we found for the free electron metal in last class, which is a constant times the square root of the energy. But before, this EC was 0, this was a constant times the square root of the energy, essentially, and we somehow have an expression for this constant here. But the square root of the energy is when the energy start from 0, but here the energy of this band doesn't start from 0, it starts from EC. So to make it honest and real, you have to really, again, this graph to the side, this is the density of states, this is the energy, and this axis here is the density of state, and you have something that goes like the square root of the energy, but starting from the bottom EC, not from 0, okay? So this thing over here corresponds to exactly this equation here. So now I have to, tell me.
I'm actually left with a slight a question, to be honest, because regarding the last thing you said in the previous slide, well, one could assume that, of course, the energy is going to be determined by the temperature in the material and, of course, the energy gap.
Yeah.
But does that relate to, for example, the property of certain materials like metals to expand and contract under certain temperatures?
No, really, the contraction of the metals it's a different process, because now a dilation or contraction of a metal as a function of temperature has to do with changing the position of the ions. What does that? It means it changed this distance here, okay?
All right.
And so this is the equilibrium distance that has to be changed or displaced a bit. And for that to happen, you need to introduce an effect which is a nonlinear effect, meaning that you have to, in addition of considering a square root, not square root, considering that the potential between the atoms can be modeled by a parabola, meaning this thing that you have, this spring thing, the energy is 1k x squared with respect to the distance, you have to add an additional term. If you add an additional term to the energy at higher temperature, that will allow that the central position of the atom is actually displaced to larger values of R. So that phenomena is slightly different, meaning now only the temperature, what it's doing here is actually lifting the energy. Essentially, if you actually warm up this material too much, what will that happen? The electrons will start to come out of the material because we'll have enough energy to actually leave the confining potential of the box. And that's exactly what that's how television works at the beginning. You need a filament. When you have a filament inside the tube when the displays were not flat, you need a filament inside, and that filament you put enough energy to it so the electrons come out of this filament, and those are accelerated and actually hit the different spot on the screen and produce these nice images that we used to see. That is so the thing is, the raising the temperature only raises well, no, raising the temperature does everything, but what the focus here is simply on the effect on the electrons. Okay, you're right that this if I have a material and they will change it, definitely the equilibrium position, but that is not the case. This is not the focal point of what I'm trying to say here. Okay.
Understandable.
Okay. So now what I'm trying to get at is, before I calculated the probability of having an electron here, and now I'm saying, look, we can actually calculate the actual total number of electrons in the conduction band. Because all the electrons in the conduction band, if I know the density of the electrons in the conduction band, I will actually multiply that by the charge and the velocity, and I will have a current. That's what it is. And how do I get a velocity out of it? I put an electric field on it. Okay, so I could calculate very easily a current based on the density of charge carriers in the conduction band. And so that's why this number here is very important. This calculation that I'm doing here, I said this is the total number of electrons in the conduction band, and I calculate by integrating from the bottom of the conduction band to infinity the probability of having an electron at a certain energy. I'm sorry, the density of state, the number of states with a certain energy by the probability of the state multiplied by the differential of energy and sum overall energies. Okay, and if we do that with an expression for the energy like this, and we actually calculated that constant during last class, and turned out to be something like this, where we had in this position here the electron mass, and that is the free electron mass. When you put the electrons inside a metal, inside a solid, you have to think of an effective electron mass, and the effective electron mass is actually smaller than the actual mass of the electron. So these are details. I'm not gonna ask you about this. I just want you to know that exists. It's the same as we did before, but this is not exactly the same mass. The effective mass inside the solid is different than the mass of the electron. Okay. So in silicon, the effective mass is almost 1.08, the free electron mass. In gallium arsenide, it's much smaller. Okay, so this constant here in the front is changed when you do the integral, but it doesn't really matter those details. The only thing that really counts is this total expression. The n of t here, the number of electrons that you actually find in the conduction band is some sort of a number that is almost constant as a function of temperature. This is, you can call it a naught, and this is the exponential factor that is the ruling thing. This is e to the minus beta, meaning the conduction energy band minus the Fermi energy divided by kT. So actually, to know the electron, to know the density of states, or not the density of states, the density of electrons in the whole band here, the only difference that I need to know is the difference between the conduction band and the Fermi level. Okay, this difference. So if I know the difference between this guy and that not guy, I know all the electrons that are, all the density of electrons in this band. Okay, this is something that is relevant. This value over here is equal to E gap over 2. Okay, because this is E gap, the gap is the difference between this and that. This is located in the middle, so this is E gap over 2. Now we come to the realization that when we let me go to the picture, because the pictures are more clear first. When we excite electrons into the conduction band, see the gray part here is where the electrons are, and this here is when we're leaving holes behind. But what happens is these holes can actually move as the electron do. Okay, because the hole in the, this is a complete band. This is a sea of electrons. It's completely filled with electrons. And when you take one electron and you put it in the conduction band, it's like putting a bubble inside a bottle that is completely filled. So you have the bubble there, and now you can watch the bubble move inside. This is exactly what happened here, meaning the bubble is not what is moving, it's all the liquid around the bubble that's moving that gives you the impression that the bubble is an object that is actually moving. You know, it's all the water around what moves. That this is the thing that have mass. The bubble is, you know, but it has a mass associated with it also because it's the mass of the surrounding media that goes around. Okay, so the holes here is in the language of quantum mechanics is a multiple particle excitation of the free electron gas. We have the gas and we have the actually one of the electrons is actually removed from here. We have a decrease in the density, but this guy is free to move in this sea of electrons. Okay, so when you actually apply a field to a system like this, if you apply a field, and a field will have to be this way, pointing and to the right of the page, okay, that will make the electrons move in the direction that they are pointing. You know, if I put the field that way, the electrons will move the other way, okay, because the charge these guys have is negative. But if I have a positive charge, this hole, I could think it as an object that has a positive charge, because in that way it's a positive charge in a sea of negative charge. Okay, so this positive charge, when I put an electric field like this, here it is, in this direction, it will move in the positive direction. So when I would like to calculate the current in a system like this, produced after, well, I could excite, for example, the electrons through the band gap by shining a light. Okay, and I shine light and I have electrons here and have holes here, and I put an electric field and I can measure a current. And the current that I will measure will be the sum of the current of the holes plus the current of the electrons in a semiconductor. You don't get the same effect on metals, because in metals you don't move. You only move charge carriers that are electrons in the metal. You don't have the effect of emptying a band, because you simply excite an electron to a higher level, and there's no electron moving anywhere, meaning it's only electron. The dynamics can only be explained with electrons in the case of a metal. For a semiconductor or an insulator, you need this model of electrons and holes to properly describe the conduction phenomena. Okay. So I've already explained this. The absence of an electron promoted to the conduction band can also carry a current. The current, the charge of this hole is a positive charge. They are also fermions. Okay, so they follow the Fermi-Dirac distribution. The mass of the holes is in general different from that of the electrons. Okay, it's a different mass. Because if you have an electron hole there and you apply a magnetic field, this positive charge will start to move, and it will move roughly some sort of like an electron, because you have to move all the electrons surrounding that hole. Essentially, that's what you are actually moving. But that gives the impression that this particle is moving, and the acceleration of velocity that you can give to this particle is somehow linked to the electric field. So you can define a mobility of holes in the same way that you can define a mobility of electrons. Okay, so this hole is a bubble of air, you know, in a liquid made up of electrons. And if it is a bubble, it must have a positive sign. So I could actually, following the same procedure as before, I could get that now that the density of holes in the valence band is equal to a different number and 1 times this exponential. Now, remember that these are like bubbles. So what happens with the bubbles is like, here's the diagram, they like to stay on top, okay? The bubbles like to stay on top. So if I give some energy to this guy, let's say I give energy, this will go down. If I release it, it will come up again, okay? It's literally a bubble in this system, okay? So these guys will have a higher energy when you are pushing them down. It means that the ground state for the holes, if you have a ground state for the holes, they would like to be at the top of the valence band. So if you actually raise the temperature of this thing, you could actually find holes thermally excited down here to a higher energy level. So, oops. This is the meaning of this. So you have the number of positive charge of holes in the valence band is going to be some sort of a constant times an exponential that now considers the difference between the Fermi level and the valence band. Okay, the Fermi level is right here. So I take, this is the value where I measure the exponential. This is a thermally excited process. That means that the thermal excitation will go from the Fermi level to this level here, which is the conduction band. And if I do the whole integral, meaning the whole integral recovers only the valence band effect here. So you can see that this P of t is actually equivalent to this N of t with the exchange of the conduction band and by the valence band, but also the change is sign. The sign is changed. The sign is changed because this must be a positive number. And for this to be a positive number, it means it costs energy to actually excite a hole down the band, okay? As it was so obvious that it costs energy to pull an electron up, pulling an hole down also costs energy. So this is why the exponents here changes sign, okay? So this is a positive value, so everything is thermally reduced by, well, there's something missing here. This is the KBT. It should be the same as this expression. I didn't put the beta here. That's a mistake. I need the beta on front here, okay? Second mistake on this transparency, okay? So I need that. So this is divided by KBT also. So this is a thermally excited process. And the sign of this thing is actually reversed from the sign of the holes, okay? This is relevant what comes next. And, you know, I want to consider now a device. And let me see, is that so? Yeah. So I'm gonna try to make something up with germanium. Germanium would be my semiconductor this here that has Z equals 32. And germanium behaves like the gap in germanium is about 0.7 electron volts. It's lower than than silicon. And it also has this peculiarity that the band is completely filled, meaning it's the model of the original model. This is the model for germanium, okay? So I have a completely filled band and this is empty. So I said, you know, I want to do something like make a device with this thing. You know, if I make a device, I have to sort of put some electrons up here, but I don't want to do that with the well, how could I excite electrons? Well, I could use light. I told you before, if I shine light in here and I give them enough energy to actually jump through the gap, the electrons in the valence band will be optically excited into the conduction band. No problem. The other way is to thermally excite them. Just heat up this thing. If you heat up this thing, there's a final probability that you will have charged carriers up here. Okay. But these numbers, even at 0.7 electron volts, if you actually calculate this, at room temperature, KT is equal to 0.025, is 25 millielectron volts. The product of the Boltzmann constant times the temperature at the room temperature is 0.25 kilo electron volt, not kilo, 0.25 millielectron volt. If I multiply this by a difference like it's 0.52, this is also an exponential that gives you a very small number. Okay, that's as we saw in the example before. So even at room temperature, you will have very few charge carriers up here. If you want to have more charged carriers up there, you introduce impurities that add electrons. How's that? This is why we get into the periodic table here. And how does this come about? This guy, for example, here is an arsenic atom. An arsenic atom compared to a germanium atom it has one more proton and one more electron. Okay, so if I have a big crystal of germanium and I put inside an arsenic atom, what I will be doing, I will be, essentially from the outside, it will be by putting a big germanium atom plus one electron. And that is very significant because that electron in this germanium crystal will have to go into the conduction band if it is excited, okay? You have one electron that is missing. Well, not missing. This is what happened. This is the germanium crystal. You have four. What are the four electrons in the germanium? Is this guy, the 4s squared, 4p squared. So it's 4s squared, 4p squared. Those are the valence band electrons in germanium. So you have four valence electrons, and are these guys here. And in the chemistry model, they are not contributing to anything because what they are doing is they are binding germaniums to germaniums. Okay, so you need this electron forming covalent bonds to all the crystals, to all the elements in the crystal here. So each one of these guys, it's actually bonded to four other guys. Okay. And the structure that this thing has is the structure of diamond, actually. And I told you a bit about that before. So these guys are forming the covalent bond, so they are not available to participate in any conduction process. And now I put this arsenic guy here, and this arsenic guy looks like a germanium plus a proton. You can think that this is the germanium plus a proton plus this extra electron. So essentially, you could apply in some sort of superposition. You can actually think that what you generate here is a plain germanium crystal, perfect, with something that looks like a hydrogen atom associated to one of the germanium atoms. Why a hydrogen atom? Because the extra proton of this arsenic will be linked to this extra electron of the arsenic, and the rest will look like germanium. So essentially the difference with respect to a perfect germanium crystal will be this extra proton added here of the impurity and the extra donor electron. this cartoon here is a bit misleading. Okay, it is a bit misleading because the actual radius of the donor electron with respect to the arsenic impurity is very big. It's almost like 5, 10 to 15 unit cells, meaning you have many germanium atoms in between this electron and the ion, actually. Okay, so it becomes a very delocalized wave function around the impurity. Okay. Now, these impurities actually, if you actually look at where they are in the energy diagram that we have drawn before, here we have the valence band, here we have the energy gap, here we have the conduction band, and we have for each one of the donor levels, we have here it's something like this. Okay, so here we have this equivalent proton with an added electron, but the actual orbit of that thing is a very big orbit, so it's very loosely bound to the proton. It's not like the electron in a hydrogen atom, but it's more like a very high excited electron in a hydrogen atom. And how excited it is? Well, it happens that when you put arsenic on germanium, the difference between the conduction band minima and the position where the energy levels of the donors are is of order 10 milli-electron volts. Okay, 10 milli-electron volts is pretty low, and now you have an excitation thermal energy which is of the order of 25 milli-electron volts. Wow, twice that value, meaning essentially you can depopulate all these guys here and transfer them at zero temperature. This guy will be here and the conduction band will be empty. If I start raising the temperature to a few Kelvin, some of these guys have a higher probability of being here. These guys will never make it at that temperature, meaning that this will be very low here. Okay, the valence band will not make it up here, but these guys are fine. And now I'm exciting them to the conduction band, which is perfect, and at room temperature, the thing is almost all of these guys will be out. So at room temperature, if I have a doped semiconductor, this is a dope. This is what is called n-doped semiconductor. You can get, in this case, an n-doped germanium. You will have germanium that has the possibility to conduct electricity, depending on the density of the guys that you put in. What is the density of conduction electrons in doped silicon? Well, it will depend on how many donors you have you put in. So the density of donors will somehow influence the density of electrons in the conduction part. Okay, so this is a way to actually a perfectly intrinsic semiconductor. Intrinsic means with no pure semiconductor. When you put an impurity in, the impurity can contribute charge. But this is not the only one case. We can also have something that you can actually contribute things that will accept electrons. Okay, this is something different. Let's go back to the table here. Look, now my proposal is let's instead of putting an arsenic, let's put a gallium in. A gallium is a smaller it's a smaller atom there. It's almost like a germanium with a positive. If we think in the way we actually solve this problem, here we thought of this as a hydrogen atom, a hydrogen-like atom. Here we have almost like a hydrogen-like atom if we compare with germanium, but now with the charge of this guy being, it has to reverse the charge. This has 32, and this is almost like having a positive charge added to germanium. Okay, and that's exactly what happens in this particular case. You have this gallium atom here. This gallium atom is almost like a germanium plus a positive charge, and you will have an electron. Then, well, it also has one less electron here, so it has a hole. Okay, this thing is contributing with a hole, and you know there's one electron missing from the whole picture here, because you need this electron to actually bind this atom to the nearby germanium. But you know what happens is that this hole here can be actually filled by this electron here that is participating in the bonding of these two germanium atoms. And well, that jump will make that this hole is movable then, because it could jump to another place, then jump to another place, and somehow makes an orbit around around this ion here. What is the? Let me check again. Yeah. So this guy over here has 32 protons, and this one has 31 protons. If this has, so how do I express a gallium atom in terms of a germanium atom? So a gallium atom is then a germanium atom with a negative proton, essentially, in this position. It's a gallium plus a negative charge I'm sorry, it's a germanium plus a negative charge in the position of the germanium gives you a gallium atom. So in the case of this impurity, you could think that this hole will be sort of trapped as a hydrogen-like thing, with the thing that the hole will have a positive charge, yeah, and the actual impurity will be a negative impurity charge, but the equation of motion will be almost the same as it was a hydrogen atom, with the charges reversed between the electron and the proton. Okay, so if you do something like that, you can actually discover then that the way to excite, to generate a hole, where would the hole go? The hole will go to the valence band. And how this excitation occurs? This excitation occurs because one electron from the valence band is actually promoted to this acceptor level. So this here is an acceptor level. This guy wants to, there's an electron missing here, it wants to accept an electron. Where does it happen? It gets it from the next neighboring guy. It makes a jump. But where was this guy before? This guy before was in the valence band, it was an electron. And so now we have a hole in the valence band due to this acceptor level. So we have these two pictures. We can put negative charge. It's an N-type semiconductor by attaching something that have more electrons, and the one that have a missing electron, it's an acceptor level that actually removes electrons from the valence band. But this valence band hole can now move, can now jump. So I could make the charge carriers in germanium being positive if I have acceptor levels where you can excite these levels by a small temperature, and the actual thing that will be moving inside the actual charge that will be moving will be a positive charge. in the case of a p-doped semiconductor, and in the case of an n-doped semiconductor will be the electrons. Okay. So this has been done technically for a long time, and now you could actually think of forming a device by bringing a p-doped material together with an n-doped material of the same material, of what a p-doped piece with an n-doped piece, okay? And bringing them together and see if we can form some sort of device. Because this would be a singular electronic properties of the system. If we look again here, before, when we had an intrinsic material, the Fermi level of the system was in the middle between the occupied levels in the valence band and the unoccupied levels in the conduction band. But now you could think that the Fermi level is right in between the acceptor levels and the valence band. Why? Because this is where the electrons are. The Fermi levels is down here, and the first unoccupied levels that the system can have is exactly at the acceptor level. So with the same logic that the Fermi level here is in the middle of the band, the Fermi level in this case is in the middle between the acceptor level and the valence band, exactly in the middle, just to compensate for the excitations of the electrons. Okay. Well, the same thing happens on the other side. See, for this piece of material, the Fermi level will be exactly here, because the excitation now is coming from this state to this state. So the Fermi level should be in the middle between where they are. At zero temperature, this guy will be down here, and the first available state to be occupied will be in the conduction band. So it means that this guy will have that excitation energy. So the Fermi level should be in between the band gaps, right there. Perfect. So now when I form the materials, and here are the donating levels. This thing is the donor level, and here are the acceptor levels, and the Fermi level is, you know, right there at the bottom of the band, because this is a very narrow difference, and this is a very narrow difference, and the Fermi level in this case is down here. This side here, this is, I should have written it down. This is a p-type, and this is an n-type. Okay, well, it's there. This is n-type because n stands for negative and p stands for positive. Okay, so this has added negative carriers that if at room temperatures, I will have them all excited here. So I will have electrons excited at room temperature here, and I will have holes excited at room temperature here. Okay. Now, this doesn't mean that this guy is negatively charged. This piece is not negatively charged, because you have to remember that we put in positive ions in here. Okay, so the total charge of this piece is neutral, and the total charge of this piece is neutral because I added positive ions here. I have this sort of mimicking the hydrogen atoms. Okay. And now in this case, I'm mimicking the positron or something. No, I don't know. And an atom with a negative ion in the core, okay, to bring this mobile charge that are the ones that are moving in this case. So this is the picture before we get the two materials together. But you can imagine what will happen when we put them together. We put them together, and then we have these guys on top here, the electron, seeing those holes down here, something very attractive because they can recombine. So this guy can fall down here and produce a photon, meaning they can recombine and produce a photon, because before these guys, they cannot get down here because you know, the advantage of getting down here is there's no room. First of all, there's no room to get down here. They only can get down here because there's room here. The advantage of getting down here is almost non-existent because they are thermally excited from this place, but it will definitely lower the energy of the system if I actually can get this electron to recombine with this hole in the p side, you know, and this is exactly what happens. So these guys start to recombine with each other, and they generate a region where there are no carriers. So these are the holes here that could move in the valence bands, and this is the electrons that could move in the conduction band in these two chunks of material. But down here, you found a recombination, and the question is, why does this process don't go on forever? You know, all these guys would like to recombine, because we have to remind them that linked to each one of the charge carriers that we had here, we have a positive charge. So the positive charge or the fixed charge of the impurities, they don't move, they don't go anywhere, they don't recombine, they are there. So there's positive charge in this side linked to the electrons that actually recombine with the holes, and there's negative charge associated to the guys around here. So essentially, in this region here, we generate a field. What does the field do? The field points from the positive charge to the negative charge. If I put a positive charge here, what it will do, it will try to go that way, okay? So that charge, this field over here, this region, this region, there's a region here where it's an electric field induced by the permanent charge of the impurities in this this is a carrier-free region here. In the carrier-free region, you generate a field, an electric field. And what does it do? If for this electron, it will, if an electron try to get into this area, it will push them away that way. If a hole tries to get into here, it will push it that way. So this is the right direction. So somehow, the fact that you generate this field here makes this the probability of this recombination reduce and eventually stop. How does this recombination stop? It stops when, this is like a machine. Let's say you recombine one electron here with a hole here, and when you recombine that, you generate a photon. And what does it do, the photon? Well, the photon could be enough to actually hit this other electron with enough energy to jump across this barrier, get to this side, and decay. When will the process be finished? The process will be finished when the height of the barrier that the electrons have to go through is equivalent to the energy released by the recombination of an electron and a hole. Okay, so this is a reason why this process has gone, because the electrons in the N and P see an electric field separating them, and this electric field, the magnitude of the potential that has appeared here, must be equal to the difference in energy. E times the difference in the potential here must be equal to the energy of the gap. Okay, so this is what I have written here, and now I am changing the diagram because this diagram is unfair, because it doesn't. If this is an energy diagram, it should show the potential too. What are the potentials of the carriers? Okay, and you have to be reminded that in this sort of diagram, the the lowest energy for the carriers are when the electrons are in the bottom part. If I want to excite an electron, I have to spend energy to move it up, okay? And the same thing with the holes. The holes are like the bubbles, they are floating in this diagram. If I want to excite an electron, for example, to this depth here, I'm sorry, to excite a hole, I have to, give the hole this much energy to actually get to this level, okay? So this is what happens, and this is how the equilibrium situation occurs. And I wrote something down here because I guess I understood this after I actually draw this diagram here. This is for the recombination process to continue, the energy delivered by the recombination, E gap, has to be greater or equal to E delta phi, with delta phi is the difference in potential between this level here, the Fermi level here, and the conduction band minima in the p side, because otherwise this guy, the recombination, it's like a machine, okay? If the energy gained by recombining this electron with this hole is good enough to actually give enough energy to the next guy to surmount this let's say it gives a lot of energy, it can get out here, it can climb and get down, and the process will continue until when? Until the energy that I can gain by making an optical transition is not enough to actually go over the hump here. So I cannot raise these guys above, okay? That's it. So, this energy here, the difference between this guy and this guy, remember the Fermi level here is essentially at the bottom of the band on this side. So you generate here the depletion region, depletion because there are no charge carriers there. There's only charge carriers in this side and in this side. But anyway, if there are charge carriers, these charge carriers could move. And how do they move? Well, if I thermally excite this guy and I give him enough energy to get to this level, they could actually move across. And the density of electrons above this level here is going to be just the thermally excited levels, and that the current that I could drive in that direction will be proportional to that number. So the number of thermally excited carriers above this level. For the holes, the same thing in this side. For the holes that have a thermally excited energy above this level here, I can get from here to here, it will means that it will move in that direction, okay? So this is the main current associated with the electrons. That is the main current or process associated with the holes. And then there's the minority carriers. If I could also have electrons going that way, if I actually can excite an electron from the valence band to the conduction band in this side. So this guy is also going to contribute to the current, but in the opposite direction to these electrons here. So this will have a minus sign with respect to this guy. But I also have the holes here. I could excite, how do I produce a hole here? Well, I excite an electron through the band gap of the semiconductor and generate a hole here. So these are the four processes that I have. I have a negative current going that way, a negative current going this way, a positive current going that way, and a positive current going the other way, okay? Now, this current here is much smaller than this current here, okay? Why is that? Well, not really that different, huh? Because, no, I take it back. Yeah, that was right. Why is this current much lower here? Because these guys, to get this electron up here, I have to excite it from the valence band. To get the electrons up here, I only have to excite them through the donor level difference. This is the excitation energy that I have to break. And this is a large number of electrons here and a small number of electrons here. The excitation of this electron, I need to excite this electron to this level. So the exponential factor of this electron and these electrons is the same to actually excite them to get to this level. It's the same excitation energy or barrier that I have to excite this guy to excite this guy, because this excitation level is equal to E gap. But there's a lot more of these guys than these guys. So this current, the current of electrons going that way, is much higher than the electrons going that way. But this, if this thing is open, it's an open circuit, the total current should be 0. So essentially what happens is that the current of electrons going that way is canceled by the current of holes going this way, okay? And this is what I have here, okay? So this is I said I1 going right. Going left. This is going left. Left is 1. No, I have this. Again, this thing is misleading again. I1 is the current going in that direction. What does it do? This takes these electrons here and excite them to this level. What is the level that it needs to be excited? It needs to be excited by the energy of the gap, okay? Which is E conduction minus EF, okay? So this is the exciting level. This guy over here, I know that I have to excite it through the gap. So this is I2, and this is I2, it's going to the right. I2 is going to the right? No, this is left and this is right. And what do I have to do with this guy? I have to excite it over this whole energy difference. No, this is completely wrong. Okay, what do I have here? Why is this thing wrong? These are all electrons. This is 2, what I have here, and this is 1. This is the way to fix it, the thing, okay? Otherwise, too many changes. 1, let's analyze 1 first. 1 should go over this E delta phi. This is the excitation energy that is coming from the bottom of the conduction band in this side. So this is 1 now. So it's that, and this is the excitation energy. Perfect. For this guy here, I have the difference in the excitation energy, the difference between the conduction band and the Fermi level. So it's the excitation from here to there. So this is excitation for this current. So this is 2, and this is 1. Okay, so the numbers are mixed up here. So the currents are proportional. This is what I'm saying. The currents are proportional to the number of carriers, and similar cancellations occur for the holes in the case of the thing not being connected. When I connect them, like with a power supply like this, I put this guy a negative end of the power supply in this side and a positive end of the power supply in this side. What do? I actually reduce, by doing that, I reduce the barrier that these electrons have to go through. So I take these guys and make them higher here. I put them higher because I raise the voltage. This is I can change the voltage in this power supply here, V. So essentially, instead of these guys having to go from down here to up here, I actually move the two things. They are like this, and I move them like that. So now the energy that these electrons need to go to overcome to get to the other side are smaller, okay? So let's see if the current is right. Yes. Now I1 going, this is the 1 process. I1 going that direction is N naught times e to the minus beta E gap, which is the same as before, minus EB. Now before was the E gap, and now it's E gap minus EB, the thing that I have moved this whole level up now. Before, if you can see that, the Fermi level was common to the two sides. And now I have this is not in an equilibrium situation because I have raised the energy level on this side with respect to the energy level on the side by E times the applied voltage. And this has reduced the barrier that these carriers had to overcome to get there. So the I1 going in that direction is reduced by EB, but the I2 going in the other positive direction remains the same as before. So the I2 this is I2, is the difference between EC minus EF, and this is beta E gap, okay? Remember that this thing had changed. This is I2 and this is I1, okay? The same thing I can do with the holes. And now, I have a net current. This thing actually developed a net current. And you can see it's easier for these guys to move that direction, and it's easier for this guy to move in this direction. And when these guys move in that direction, they generate a positive current. When these guys move in this direction, they generate a positive current, and the barrier is actually decreasing the same way. The barrier for the motion from the process we call 3 here is moving this guy this direction. What I have to do is excite thermally this particular hole and get it to this level so it could move in this direction, okay? If I add up everything, what I find finally is this is the adding, if you take in proper consideration of the signs of the currents and whatnot, this is the expression that you could get. And then the actual current through this circuit here is going to look like that. It's going to look like a front value times e to the beta EB, the electron charge, times the applied voltage minus 1. That in a bracket. So I recognize that everything in front here, I call that I naught, and I plot the current of this guy as a function of voltage. And it turns out that this is a very sort of steep exponential going that direction. And if the voltage, look, when the voltage is negative, I actually, meaning it will be the other way around, it will be moving this thing down, pulling this guy further down. So it will be very hard, very difficult for these guys to actually get to that, more difficult for those guys to get to this side. And the same thing will happen to this guy. So the current will be exponentially suppressed, which is exactly what happened here. So I naught, if this is very negative, meaning this will go to 0, so the current will go to minus I naught, which is what I have here. And this over here is a rectifying device. If you can actually idealize it and put it like that. So when you apply a positive voltage, you get current, and when you reverse bias it, you get no current. This is it, okay?
Small thing, not to really interrupt, but I think we may have gone a little bit further than the schedule.
Oh God, I gotta wait. Oh, sorry. Let's leave it here then, guys. Okay, I'll finish this explanation next time. This was the last biograph anyway, so my apologies. I get carried away with this thing. Okay, so this is it for the week, and enjoy the weekend, guys. Okay.
You too. I hope you have a very good day.
Okay, thank you. Bye bye. Sorry about this.
No worries.